Hi everyone. So welcome to a new lecture of Calculus 2 series. Our topic for today is trigonometric substitution. So this topic is basically it's also substitution by utilizing the trig functions to substitute them for the variable given in the problem. So to elaborate on this, let's start with an introduction, and let's see at an example of type. Let's say if I have an integral of the form dx over x squared plus 1. So you may realize that a problem like this, we already know how to solve it, and that is simply equal to tangent inverse of x plus c. And that's absolutely correct. But let's see where this came from. So we will be deriving this formula. Okay, so to do that, I'll be utilizing each time this right triangle. So let's say this is theta. And if you look here that I have x squared and I have 1. So if I put those on the triangle that I drew, so let's say, for example, if this side is x and this side is 1, then using Pythagorean theorem, then the hypotenuse is going to be x squared plus 1 all underneath square root. So let's see. From this, I can say that sine of theta equal x over 1. Or, my bad. I meant that tangent of theta equal x over 1. Simply, it's an opposite over adjacent. So x equal tangent of theta, and dx equal secant square of theta d theta. So if I substitute this into my integral, so the problem would become, well, dx is simply secant square of theta d theta. X square is simply tangent square of theta plus 1. Well, we already know that tangent square of theta plus 1 have a denominator. This is simply equal to secant square of theta. So I will have secant square of theta and denominator, and secant square of theta in numerator, d theta. Well, then this is straightforward. All I have is integral of 1 times d theta. And that's simply equal to theta plus c. Now, looking back at the triangle, if I have x equal to tangent of theta, then simply theta equal to tangent inverse of x. So the final answer would be tangent inverse of x plus c. And that's basically where this formula comes from. So this is basically what I mean by trig substitution. And as we will see, this is very, very powerful tool. And it has a lot of application in engineering and science. So it's really, really good to have a good handle on this topic. Let's see. So let's take an example. Let's see. So if I have an integral of the form 9 minus x squared underneath square root divided by x squared dx. So looking at this, I have 9 minus x squared, so square root of 9 is a 3. So I can say the hypotenuse is a 3. And I can choose any of either the opposite or adjacent to be x, but I'll choose the opposite to be an x. Then the adjacent would be simply 9 minus x squared underneath square root. So looking at this, the easy way to go about this is that sine of theta, it's opposite over hypotenuse, so x over 3. Then from this, I can say that x equal 3 sine of theta, and dx equal 3 cosine of theta d theta. Let me use a different color. So my problem would become 9 minus x squared is simply 9 sine square of theta. And dx is simply 3 cosine of theta d theta. And x squared is 9 sine square of theta. Then if I factor 9, I will have 1 minus sine square of theta. And here, 3 with the 9 cancels. I will have cosine of theta d theta divided by 3 sine square of theta. 9 will comes out as a 3, and 1 minus sine square is cosine square, but it's underneath square root, then this will becomes cosine of theta. Then I have another cosine, and I have a 3 sine square of theta d theta. So 3 with 3 cancels out. I simply have cosine square of theta divided by sine square of theta d theta. And that's simply equal to cotangent square of theta d theta. And we already know how to handle this. So cotangent square of theta is equal to cosecant square of theta minus 1 d theta. And this is equal to simply negative cotangent of theta minus theta plus c. So now we need to put everything back in terms of the original variable, which is x. So from this, let me choose different color. So we know that theta is simply, so if I know that sine of theta equal x over 3, then theta is simply equal to sine inverse of x over 3. And what else? I have cotangent. So I know that cotangent is 1 over tangent. So tangent of theta equal x over 9 minus x square underneath square root. Then simply cotangent of theta is 9 minus x square underneath square root divided by x. So now all I need to do is substitute these two values back in my original integral. So our final answer would be what? Negative 9 minus x square underneath square root divided by x minus theta is sine inverse of x over 3 and plus my constant, which is c. So that's the final answer. So as you can see, this has really good applications to solve a problem of the form, as in this problem, which is 9 minus x squared underneath square root divided by x squared, and solving it in other way, like directly dealing with x, would be very tough. Let's move on to another problem. Okay, this is an interesting problem that I have here. So let's say if I need to find the area of ellipse. What I mean is that the area that's enclosed by ellipse. So let's say I have ellipse here, and let's say this point is A0, and this point is 0B, and this is X, this is Y. So we know that ellipse has an equation of the form x squared divided by a squared plus y squared divided by b squared, and that's equal to simply 2, 1. So this is not in the form that we can deal with right away. So what we can do is that solve for y and find an equation for this curve basically, and then go from there. So let's do that. So if I multiply both sides by b squared, then I will have b squared over a squared x squared plus y squared, and that's equal to b squared. Then y squared simply equal to b squared minus b squared over a squared x squared. So y equal to plus or minus b squared minus b squared over a squared x squared. Since yeah, we always like to deal with a positive number, so I will take the curve of the positive one and say b minus b squared over a squared x squared. It's important to note that, well, even though my drawing for the ellipse is not to scale, but we know that there's 4 quadrant, and all these are symmetric. So all I need to do is to consider integral limit over 1 quadrant and multiply that result by 4. So let's do that. Let's set up my integral. So area would be 4 times area of 1 quadrant. Then area would be 4 times integral. So what integral that I have? B square minus B square over A square X square underneath square root dx. So I'm integrating with respect to x, and as I can see that in the quadrant, x goes basically from 0 to a. Okay, let's do some more simplification on the integral. So area would be 4. Let me put the limit of integration 0 to a, 0 to a. And then let me see. If I factor b square over a square, from this, then simply I will have here a square minus x square. If I multiply now, a with a cancels out, so I have b square minus b square over a square times x square. Okay, so this is fine. So integral 0 to a, this will comes out as b over a, and then I will have a square minus x square dx. So this can be also solve it using trig substitution. So if I have an triangle, I have my theta here. Since we have a square minus x square, I'll put my a there. Since a is a hypotenuse, then I will choose my x here, and simply the adjacent will be a square minus x square underneath square root. And from this, I can derive the substitution that I want to use. So so what's the trig identity that links x to a? Well, obviously that's sine of theta. So sine of theta equal x over a. Then x equal a sine of theta, and dx equal a cosine of theta d theta. Then my integral will become for integral b over a square minus x square is a square sine square of theta Let's draw just this line here. And dx simply would be a cosine of theta, and here d theta. And let's now work on the limit of integration. So when x equal to 0, then a sine of theta equal to 0. Well, obviously we know that a is not 0, then sine of theta equals 0. Well, then theta equal to 0. That's the first limit. And when x equal a, then a sine of theta equal a, then sine of theta equal 1, then simply theta equal to pi over 2. And this makes sense. And here's why. We go back to the ellipse. The first quadrant, which is here, it goes from a to 0 all the way to 0b, which is first quadrant. So I go from angle 0 to pi over 2. So for that reason, this makes sense. I'm only looking at the first quadrant. Okay, going back to our problem. Then a would be for integral 0 to pi over 2 b over a. I can factor a outside, then this one will be 1 minus sine square of theta is cosine square of theta, underneath square root is simply cosine of theta. And I have another cosine here, which is another a cosine of theta d theta. Then a with a cancels out, integral 0 to pi over 2, ab cosine square of theta d theta. Well, I guess now this is in a form that we can easily integrate. So for ab integral 0 to pi over 2, cosine square of theta is 1/2, 1 plus cosine of 2 theta d theta. Then 1/2 with the 4 cancels out, you get 2ab. Integral of 1 is theta, plus integral of cosine of 2 theta is 1/2 sine of 2 theta, 0 to pi over 2. So let's see, 2ab, I have pi over 2 plus sine of 2 theta I have, which is sine, it becomes sine of a pi, which is 0. And the rest, if I plug in 0, 0, I'll simply get 0. Then this one would be ab times pi. So that is the area of the ellipse. So I hope this was clear and useful. I intend to make this lecture short, kind of just to like introduce topic and give like a couple of examples. I hope this was useful. Please comment on the video and share with others so that more and more people get the benefits of this. And also subscribe to my channel so that you stay up to date with all the videos that I upload. I would like to say also that I will make another lecture, which is going to be longer than this, to solve more and more problem to elaborate more in this topic. Again, don't forget to subscribe. And that is all I have for today. Thank you.